Hi everyone, I'm Yong a second-year PhD student at the University of Cambridge and the Kafka Institute of Cosmology. And today I would like to talk about some work with Will Colton and Jiamin Ho in using the kinetic Sunyaev-Zel'dovich effect to probe parity violation at a lower point. The universe as we know it violates parity maximally at very small scales. The standard model only have left-handed neutrinos but no right-handed ones. So one of the biggest questions is, if the universe violates parity at the small scales, does it also violate parity at the larger scale? Hence, we've been trying to look for parity violating signals in cosmology, and we have seen some hints, for example, in the Planck results in 2016, showing mild cosmic birefringence in the cosmic microwave background. More recent measurements of logical structure in the Boston DESI surveys have also yielded hints of parity violation, ranging from 4 to 10 sigmas, depending on analyses. One of the major questions is that, are these measurements robust? If they are, they should show up in other statistics that are sensitive to parity violation, and we should look for those alternative observables. So the question is, what are the observables that are actually sensitive to parity violation? The universe as we know it on larger scales is homogeneous, and that means we have a symmetry of translation invariance. Theoretical studies have shown that translation invariance is actually quite stringent and enforces parity violating physics in the scalar sector to first appear only in 4-point statistics. What does that mean is that if we try to consider a lower point statistic like the bispectrum, which is a 3-point correlation function, the translation invariance enforces this correlation function to be proportional to a momentum conserving delta function. However, because of parity violation, it only shows up in the parity-odd part of this correlator, which is proportional to something that's a pseudo vector, a pseudo scalar. That is something like a scalar triple product. Together, the momentum conserving delta function basically forces the scalar triple product to vanish identically, making it zero, and thus the bispectrum is not sensitive to parity violation. This can be shown intuitively using this graphic over here, is that when I have the translation invariance, the correlators basically, the momentum of the correlators form a closed triangle. And under parity transformation, this triangle gets flipped over here. Now using an additional rotation invariance of the universe, which we do see at large scales, basically we can rotate this triangle by 180 degrees and map it back to itself. This is a sign that you can't differentiate from the parity inverted one from the original triangle in a rotational and translational invariant universe. Means that this is statistics that is not sensitive to parity. This is why that traditionally in logical structure measurements like those done in Boston DESI, they have usually relied on 4-point correlation functions of galaxies because in counter to the 3-point function, a 4-point correlation function which forms a tetrahedron, when inverted under parity, cannot be mapped back itself in solely by rotations. This is really nice because we have a statistic that is actually sensitive to 4-point correlation functions, but it comes with caveats. It has large degrees of freedom, which makes it very, very computationally uh, costly to evaluate. And it also has been shown to be very prone to systematics. Hence, one of the biggest motivation of this work is to go beyond the trispectrum or the 4-point correlation function to see if we have better statistics to do this with. Indeed, there is, but this has been shown in Jemison and collaborators earlier this year, where they have found a way out by looking at compressed statistics. What they have basically done is to look at some scalar field, like the density field, and basically weighted them with different filters. By taking products of these fields, these filtered fields, they build something like that is akin to composite operators, which is evaluated at a single point. And you can form like 2-point functions of these composite operators, which has been shown to be sensitive to parity violation. It has been shown that these actually suffer from some contamination, but it largely reduced the number of degrees of freedom enough that this might be still a viable probe to probe parity violation at a lower cost. One of the extensions to this is to ask the question, can we directly measure these compressed statistics in the sky without using to filter them with arbitrary artificial filters? If you stare at this example of a compressed statistic long enough, you might see something that is quite familiar. This gradient of the density field reminds you something of a velocity. This is true. In fact, in linear theory, the velocity field is related to the density field via the continuity equation that looks exactly like the gradient times the time derivative of the density field. If we multiply the velocity field with a density field, usually in this structure with a 1 plus delta, this gives something which people call the momentum field, which is a vector quantity. Not only that, is the density and the is the product of the density and the velocity field evaluated at the point, so it is also a composite operator akin to the one that we looked at the previous slide. This is great because it allows parity-odd statistics at lower points, most importantly at 3 points, where I could come up with something that's like the momentum field and the times two density fields in a bispectrum. Just looking at the vectorial structure, we know that this must be proportional to a pseudo vector, which one can build using two of these momenta, like k1 cross k2. And this is the most generic thing that you can have. And this does not vanish even under the presence of a momentum conserving delta function. Coming back to the visual guide that we had, although a 3-point function maps back to itself after a parity and a rotation, if I now dress this triangle with a vector field on one of its legs, and under parity transformation, this vector maps to opposite of itself, which goes down. And this cannot be mapped back to the original triangle with the vector field also pointing the same direction using only rotations. So this is a visual hint and a visual guide that tells you that, okay, maybe a momentum density bispectrum is sensitive to parity violation. Then the next question would be, can I look for this in the sky? Can I see momentum fields in the sky? Again, the answer is yes, and this has already been looked for in the kinetic Sunyaev-Zel'dovich effect. So the name of the game is to look for momentum of electrons in large scale structure. This can be done because as the photons from the cosmic microwave background propagate through the late universe, it encounters the large scale structure, which has a lot of free electrons. This induces new anisotropies. One of them is called the kinetic Sunyaev-Zel'dovich effect. This is basically caused because when photons encounter electrons in motion, it either gets redshifted or blue shifted depending on if the electrons are moving away from us or towards us. This creates an anisotropy in the CMB temperature, which is proportional to both the line of sight velocity and the electron density, which together basically gives you the line of sight momentum field. This you may think is a small effect, but indeed it's not. In fact, it dominates the CMB power at large scales after the primary CMB has been damped by silk damping, and is the dominant contribution among lensing it's even higher contribution than lensing at very small scales. And we will be able to see this very closely in coming results in the Simons Observatory and also the South Pole Telescope. So we basically this kSZ galaxy bispectrum basically gives us the momentum density bispectrum that we were seeking after for in the previous slides, which gives us access to the trispectrum. If you're more an aficionado of Feynman diagrams, this is basically saying that we have a source of a trispectrum, which for two of its legs go into density fields modulated by a transfer function, while another two of its legs get modulated by this momentum composite operator, giving us the kSZ field. Or in other words, when we look at the kSZ galaxy bispectrum, we are implicitly summing over all the possible trispectrum that has another triangle with the kSZ legs fixed and summing over them. Most importantly, this is not just a random statistic that we just came up with. This bispectrum is actually already widely tested and used in the kSZ community for the parity-even sectors. For example, here is a forecast for the signal-to-noise ratio of the kSZ galaxy bispectrum that people have already done for CMB-S4 on the left. And people also have been having visions of using this statistic to look for primordial non-Gaussianity, in particular local FNL. And the plot on the right is basically what can be constrained using the kSZ galaxy bispectrum for FNL. So the machinery and the framework of these measurements are already there. And what are we trying to do is just trying to hijack the technology and turn it around to use it for parity violation. So we know where to look for it. The next question is how. Looking for it naively in the sky is a bad idea because the CMB sky is inherently very noisy, especially in terms of high order statistics. So in usual CMB analysis, like higher order statistics in the bispectrum, looking for primordial non-Gaussianity, are made possible with only fast estimators that look like this. So an estimator for something like FNL may look like is something that's like an inner product between a theoretical template of the bispectrum with a filtered map of the CMB. This is inherently very slow and is scaled as L max to the fifth power. But if we do a simplification that if we only consider bispectrums which is separable, which basically means that the bispectrum can be written as a product over fields, each of them only depends on one multiple, then this can be greatly enhanced to L max to a third or to a second or a third. This is basically because the FNL estimator can be written as an integral over three maps, each of them evaluated like this. This computational cost is greatly reduced, and this is what makes primordial non-Gaussianity constraints easy to do on the CMB sky. So can we do this for the kSZ galaxy bispectrum? It is not actually that trivial. It is actually very non-trivial, yes. In harmonic space, the galaxy fields are fine because they look similar to the temperature field of the CMB, just with an additional projection around the line of sight. The kSZ signal, however, again, is proportional to the momentum operator, which is a composite operator, which means that in Fourier space, it is convolution. In harmonic space, this is basically parameterized by a Gon factor, which looks something like this. Even without a convolution and only looking for primordial trispectrum that we know are separable, the standard trick of using isotropic basis functions for the angle average trispectra basically yields non-separable results. For example, this is an example. This is something I take out from Greco's paper on lensing trispectrum, on the parity-odd trispectrum. And it basically yields like functional dependence on a Wigner 6J symbol and Wigner 9J symbol, which is not easily seen to be separable. So how do we get around this? Well, most of the problem is that we have been trying to insisting on using angle average observables. This is to ensure that everything is isotropic, but if we know that the fields are isotropic in the first place, there's no necessary need to always go to the angle average trispectrum. We can always work on the full bispectrum or the trispectrum and just take care of the non-separable couplings there. For example, one of the non-separable couplings that arises is from the momentum conserving delta function that comes from the primordial parity violating trispectrum. This basically enforces momentum conservation and couples all the four legs of the primordial trispectrum. However, we know that this can be easily written as a integral over exponentials. And any dynamical variables, for example, like those in the triple scalar product, can just be written as covariant derivatives acting on the exponentials. What you're left with is some functional dependence that looks like this, and a parity violating trispectrum that is usually separable. The parity even parts of this trispectrum, most templates have been shown to be separable in these two papers over here. And factorizability constraints in Stefanison's paper over here gives us strong hints that most parity-odd trispectrums are also separable. We haven't denoted any vector or kinematic dependence here for simplicity, but this is usually not that severe. After a plane wave expansion, this gives an antisymmetric combination of a radial derivative on some spherical Bessel functions and spin weighted harmonics or weight and spherical harmonics raised and lowered by the spin lowering and raise operators. This basically gives us spin weighted spherical harmonics, and the combinations of these basically gives us separability in many aspects. A similar expansion can be done for the Gaunt vector to be written in terms of spherical harmonics, and everything could be written in a factorizable form. We've tried to do this as much as possible, and we are going to spare everyone the mathematical details. But for example, we have done this explicitly for a local shape, which looks like this. This has been proposed by Colton et al. In 2023 and has been the benchmark for many simulations and tests for parity-violating statistics. We have found both a factorizable estimator and also a factorizable Fisher information. Schematically, the Fisher information looks something like this, which is an integral over 4 maps and the integrand over 4 functions that look like this. These functions are basically products of degree L polynomials weighted by some number on a grid. This thing basically scales as L max. And if you look at the integrals, this basically scales like L max to the 8th. So this entire thing scales like L max to the 9th, which is not really good, even though it's separable. However, notice that each unit vector appears exactly twice. So for example, x here only appears here, and only appears and here, and so does the primes. So if we do a decomposition back into spherical harmonics, the Fisher information can be written as a single sum over one multiple. If we look at this, because we know this is basically a product of degree L polynomials, this Fisher information scales only as L max to the squared. This is very good and it's amazing for forecasting. And it's not exactly trivial to see that it can be written in this form, which was quite surprising for us, and we're very happy. Basically, this comes to the end of my talk. I'll summarize our findings and some outlooks. Basically, I hope I have convinced you that because of the nature of the kSZ, it as a composite operator, which means it's a local operator of both of the product of the density and velocity fields, is also a vector operator, and the kSZ basically only picks up the line of sight. And this is natural observable into parity violation, and it's already accessible through the already widely used kSZ galaxy bispectrum. Again, we just need to hijack whatever machinery that's already on the market and try to use it for parity violation. Because kSZ peaks at very high multiples, it's really important that we work towards fast estimation and also forecast using angular observables. So we really, really want to have factorizable bi and trispectrum that really have the right scalings. We have done this for a local type primordial trispectrum, and we really like to look into how generalized is this factorizability, and can we do it for even more models like spinning exchange parity violation models. Because of this new technology that we have, forecast for the signal to noise of the parity violation through this kSZ galaxy bispectrum is coming soon, and I hope you look forward to it. There are also some future work to know like what is this statistics actually, what is shapes that this statistic is actually sensitive to, and also if like the Sunyaev-Zel'dovich effect in scattering also creates polarization signals. And it would be also nice to see if we can locate parity violation in the gravitational sector through this. There's also questions about looking through this through simulations, and I refer you to Colton's talk in this regards. With that, it comes to the end of my talk. I thank you for your attention.